So I guess we'll be starting now. Anyone that joining will definitely get to follow up and watch the recording later after the classes. So welcome again. Today, this is the first class of our Starknet Nairobi Bootcamp. We'll be talking about Starknet, Cairo, blockchain, layer 2s, and everything you need to actually know about Starknet. And today we're having Ademola Kelvin to put us through in all this. And yeah, Kelvin, welcome to this class.
Yeah, thank you. Can you guys hear me?
Yeah, I can hear you.
All right. So, thank you guys. Thank you for coming on board. And the host has already said, we'll be discussing basically some fundamental concept about blockchain. Then we take it a step further to discussing about layer 2s, Starknet in particular, and the architecture of Starknet, and some other concepts in depth. So I want to lay emphasis on something real quick. I would like for the class to be interactive as possible. So if you have a question, just feel free to call my attention to it, and at some point I will throw questions at random too. So please let's ensure to participate, and yeah, we're good. So I'll cast my screen now. Okay, share screen. Can you guys see my screen?
Yeah.
All right. Yeah. Okay, you can also see my screen, right?
Yeah.
All right. So thanks for joining once again. So talking about blockchain, does anyone have an idea of what blockchain is? What have you heard about blockchain? What have you read about blockchain? Anybody on the call? How vast is our knowledge about blockchain? Please, if you're on the call, can you just signify with, I don't know.
Am I audible?
Yeah. Does Zoom allow raising of hands? Just drop a reaction if you're on the call, please. Yeah, please go ahead. Can you your understanding about blockchain and just give us an insight?
Good evening, everybody. So the way I understand blockchain, simply speaking, you can say it's a database that is centralized. And if you want to simplify it that way, it can be that simple, actually.
Okay. 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 Thanks for that. Yeah, nice. So you are correct. So I don't know if we have some sort of Web2 background, but basically, give an instance that you have, let's say Web2 architecture. Now you have front end, then you have your back end, and all your requests are sent to the database, which means that you're storing data into the database, right? But then having a single database gives room for single point of failure. So a blockchain is like a distributed database whereby like a distributed database whereby you have different section of database with the same amount of information. So it's a shared and distributed permanent database that is shared across multiple nodes in a computer network, like a distributed system, basically. And we know that once you have this kind of systems, that means the system is decentralized, it is secure, basically. And looking at the, sorry, please let me know if I am too fast. Just call my attention to anything you feel should be, you're not clear about. Please, are we following, please?
Yeah, everything's okay.
All right. Yeah, so to put it in the simplest term, that is like what blockchain is basically. So looking at this image now, looking at this image, you can see that we have different, let's say, I'll point to these as different databases, right, that are connected, right? And then you can have communication between Alice and Bob, and such that you have their, let's say, the result of their communication, which is a transaction in this case, stored on the blockchain, and all the nodes in the blockchain share same copy. Um, are we familiar with the concepts of nodes? What nodes are, or do I need to like explain that in depth? Okay. Okay, so I guess I'll stick more to checking the message in the chat. Sorry, give me a minute. So like we established that, okay, the blockchain is a distributed database, right, that comprises of multiple nodes running the same instance. So what is a node basically? Nodes are like moderators that build the infrastructure of a decentralized network. So their primary function is basically to allow to maintain consensus of a blockchain. So using Ethereum as an example now, right? So we have many people running several instances of node across the world, basically running the what do we call it? This Ethereum software, right? And then we know that the Ethereum software comprises of I think the Ethereum node basically comprises of the execution layer, so is it from my hand? Comprises of the execution layer, the consensus layer. So once you run the software, you are able to like participate in the network, and also be able to validate transaction and propose blocks. So that's what nodes are at the simplest level. And like we know, for every action performed on the blockchain, it involves transition from one state to another. And initially, blockchain starts with a genesis state when they launch, which is using Ethereum as an example now. Ethereum first state was like the genesis state, and as transactions were being processed on the blockchain, we kept on having transition from one state to another, right? And so to give a full context, basically, to give you a full context, so you have your nodes, and then you have a participant in the network. So let's use this image as an analogy. So you have nodes in the network, right? And then you have Alice. Alice is a participant in the Ethereum network, and Bob is also a participant in the Ethereum network. Now you want to like make a payment from Alice's account to Bob's account, right? So once you initiate the transaction, that I want so amount, let's say Alice has 5 ETH in our wallet. I want 5 ETH transferred to Bob's account, right? So the node runs the computation basically to check the validity of that transaction. Do you have the amount you claim to have, and do you have enough gas to send that transaction to Bob? So these are the things these are one of the things the network does, in particular the node does. So if you meet all these criteria, then the transaction is validated and the required amount is sent to Bob. So in all these processes, you have validation of the transaction, you have different transactions across the network being um, proposed into a block, right? And once the block is validated, it is added onto the chain, basically. So in a nutshell, there is a state transaction of, okay, Bob Alice has this so amount and our account has changed to this recent amount. Similar for when you make contract executions too, and um, probably you make an invocation, uh, probably make an invocation with payment. So there's always like management of state transition. This is what this slide is saying, basically. So transactions are blocked. So every action performed on the blockchain is a transaction, and the way we organize those transactions are like basically organizing them into blocks, and then the blocks that are validated are added onto the chain. So please, do you have any questions so far? Because I just gave a little summary of these things. I didn't like delve into them in details. Any questions so far based on blockchain, state management, transaction, and blocks before we proceed? Oh. Sure. Yeah. Sure. So is my voice? Can you guys hear me clearly?
Yeah.
All right. Okay, since there are no questions, so let's briefly talk about nodes. So a blockchain network is managed autonomously through a peer-to-peer distributed system of computer nodes, right? So like we said, nodes basically like run the network software to manage consensus, and the consensus mechanism we have to for the network to reach a state of agreement are basically like proof of work, proof of stake, and other examples such as delegated um, proof of stake and proof of authority. So these are the consensus mechanism available in the blockchain ecosystem. But then previously, Ethereum network was using the proof of work, which basically involves the nodes and the nodes, in this case miners, to solve for some complex computational math to be able to like add blocks onto the chain. But now Ethereum has transitioned to proof of stake, basically, which reduces their carbon footprint and allows for scalability. So putting all this together, right? Ethereum, it's a blockchain on its own, and to have a fully effective blockchain, you have to ensure that security is guaranteed. It has to be decentralized and also scalable. But for distributed systems can only like achieve two of these things, right? Is either you have security in check and then you have scalability, or you have scalability, or you have security in check, and then you have decentralization. So in the case of Ethereum, Ethereum is decentralized because you have close to 1,000, if not more than 1,000 of nodes, and then which means it is decentralized, and then it is secure. And looking at this, which that leaves the loophole for scalability, because imagine running instance of okay, back to this example where Alice made a transfer from her account to Bob's account. Once that transaction has been validated, every node in the network has to like run that same transaction, right? Have the copy in their own node. So we can imagine the amount of computation taking place like every day that each node has to like sync and have the same copy. So this kind of like limits scalability of the network, Ethereum in this case. Please, any questions so far before I proceed? Okay, I'll just go on. So, like we know, the Ethereum is a layer one, basically. And what are layer ones? Layer ones are like the base blockchain. Looking at Ethereum and Bitcoin now, they are layer one blockchain because they are the underlying foundation that various layer two networks kind of build upon. And for a system for Ethereum is a layer one because it includes a network of node operators to secure and validate the network, right? A network of block proposers, a network of block producers. Block producers basically means, like we said earlier, Ethereum uses proof of work as earlier, like in the later version of Ethereum, they used proof of work as a way to validate transaction and get the nodes to reach a consensus. But now we utilize proof of stake, which means there has been some sort of changes in the architecture and in how transactions are validated and how the nodes sort of reach consensus, which breeds this concept of block producers. So the blockchain itself, and the history of transaction data, and also consensus mechanism for the network. So far we've discussed what a blockchain is and how Ethereum is and its consensus approach, and what a layer one blockchain is. So looking at this, like we established that a distributed system, right, cannot possess all these three qualities, right? Then how then do we achieve scaling? So there are two ways we can achieve scaling, basically. Scaling can be achieved as through off-chain scaling and on-chain scaling. So I don't know if how many of us are like familiar with the Ethereum roadmap? Anybody? Sorry, please, I need feedback to ensure that we are following. Okay. And what do you know about sharding? Do you know about the concept of sharding? All right. Okay, so like I established that, okay, how do we scale the system? Like I said that for Ethereum, right? Ethereum is secure, it is decentralized, but then has issue of scalability. And I said there are two ways we can scale the system. We have on-chain scaling and off-chain scaling. So basically, to scale Ethereum, one of the things the Ethereum Foundation has to like do is to transition to proof of stake, and the proof of stake basically gives a roadmap to the to several other implementations. So now looking at those solutions, right? We said off-chain scaling and on-chain scaling. Looking at on-chain scaling now, on-chain scaling is basically an example is sharding, where you have the network breaks the sort of the network kind of break into 64 shards, right? And they can process transactions independently. So they can process transactions independently, right? So this kind of increases the amount of transaction that can be performed on the network. But then, like we all know, this phases might take quite a number of time, because there are still other implementations to be prioritized. Then we have off-chain scaling. Now we have the concept of layer twos. So we'll be moving into what layer twos are basically. So what is a layer two? Why do we need layer two? And discussing about the concept of zero knowledge proof and also zero knowledge. Please, do we have any questions so far? Any message on the
Excuse me, can you hear me?
all right, in the absence of, okay.
Yeah,
Okay, in the absence of any question, I'll just proceed to layer twos, basically. So layer two is a collective term for Ethereum scaling solutions that undo transaction of Ethereum layer while still taking advantage of the robust decentralized security of Ethereum layer one. So what this is saying basically is we've established that we have off-chain scaling solution, which is sharding, which is in line with Ethereum's roadmap. And also we have, on-chain, right? And then we have off-chain, basically, which talks about the concepts of layer two. So layer twos are, how layer two works basically is that they do computation off-chain. Your transaction, everything you do, they are off-chain, but then they post the resulting data on-chain, right? And then another fact to note is that most layer twos, except for sidechain, they derive their security from the Ethereum layer itself. So looking at it now, initially we said distributed systems, right? They are decentralized, they are scalable, they are decentralized, they should be decentralized rather. They should be scalable and also should be secure. And in this case, we have Ethereum, which is decentralized, which is also secure, but then has the issue of scalability. So looking at the off-chain solution now, right? Decentralization has been achieved by them, right? And also scalability. But then you can see that there's a missing factor, which is the security. So in order to make up for this security part, that is why most layers will have to like depend on layer one for security. So examples of we are not there yet. So why do we need layer twos? What are layer twos sort of like useful for? That is where like the blockchain trilemma sort of comes in, right? Where you have the system has to be decentralized, scalable, and also secure. Security in this case. So three desirable properties of a blockchain are that it is decentralized, secure, and scalable. So you might have like, okay, said to yourself that, okay, I've been using distributed system as an example. So blockchain, looking at the history basically from like years of research till now, right, we can basically classify a blockchain as a distributed system, right, peer-to-peer networking sort of architecture. So three desirable properties must be possessed by a blockchain. It must be decentralized, secure, scalable. So, but then the network achieves two of these and has a deficit in one of these qualities, which is the scalability. So the blockchain trilemma states that a simple blockchain architecture can only achieve two of these three, and then we want a secure and decentralized blockchain, right? So we need to sacrifice scalability. So I don't know if you've taken a look at other blockchain architecture, right? We would always see a reoccurrence of them achieving just two out of these three properties. I think I'm not sure. I think Solana, for example, Solana is fast. I think they are decentralized, but then it's not really, I wouldn't say not really secure per se. But then there's always a trade-off to be implemented by various blockchains. You can check out for other blockchains to see how the architectures and the features they sort of have. But primary focus for this for this class is Ethereum. So Ethereum is decentralized, it is secure, but then has scalability issues. So looking at the types of layer twos now, the layer two solutions, we have quite a number of them. We have channels, we have plasma, and then we have side chains, and then we have rollups. So remember we established that for a system for a layer two security is dependent on a layer two is dependent on layer one for security, right? But then out of all these layer two solutions, sidechain does not depend on Ethereum on the layer one for its own security. It runs its own proof of it runs its own consensus mechanism on independently, right? So an example of this sidechain is Polygon, right? We can like check that out. So now our focus basically is on StarkNet and how StarkNet sort of adopts one of these layer two solutions to help to scale Ethereum. Please, are we following any questions so far?
Yeah,
Okay,
I think there's a
I had a
question in
question
the chat too.
concerning sharding because we are splitting the chains into smaller segments. Does that mean that there will be a different exception layer for transactions and another for data storage? No, the basically, to my best of understanding is that when you have this shard, they will be running. Each shard is going to like run an instance of the EVM to process transactions on its own, right? And then once these things are done, there will be some sort of like sync at the end of the day. So there are no what does it mean? Okay. So that's the answer to that question. So okay. Thanks, Darlington, for answering that. So what are rollups basically? So in a bid to effectively scale Ethereum, there has been numerous scaling solutions from state channels to sidechain and also rollups. Whilst this different scaling solution possesses their different advantage and trade-off, rollup has been widely accepted to be the future of Ethereum scaling. So what a rollup does basically is it bundles like hundreds or let's say millions of transactions into it compresses them and then submits those submit them on chain, right? So if you have like let's say a million transaction performed off chain now, remember rollup, sidechain, plasma, state channel, they are often scaling solution, but then we are going to like focus on rollups in this case. So what rollup basically does is it performs transaction off chain, compress them, and then submit them on chain. So that is where the concept of rollup sort of comes in. So we'll still like see this in detail and how and the different categories of rollups that we have. So, okay. Any other question before I go on? Daniel, I can see your mic is on mute. Do you have a question? All right.
Hello.
So, what is Starknet? So Starknet is a permissionless decentralized ZK validity proof. Do not worry about the ZK validity proof aspect. We'll still like dig deep into that. It operates over Ethereum, enabling decentralized application to achieve scale for its computation without compromising Ethereum's composability and security. So it uses zero knowledge. It uses zero knowledge rollups, and which can process thousands of transactions in a batch that then post some minimal summary data to Ethereum. The summary data defines the changes that have been made to Ethereum state and some cryptographic proof to those changes. So what this is saying basically is, remember we talked about rollups, and we established that rollups basically makes computation off-chain, compresses them, and then posts the data on-chain. And then we have two types of rollups. In this case, we have the optimistic rollup, and then we have the zero-knowledge rollup. So the two categories have the same, they are kind of similar, but then they have their mechanism of their mechanism in which they work is different. So explaining optimistic rollup now. Optimistic rollup basically it does the computation off chain, right? Compresses the transaction and then tries to like post the data on chain. And then while posting that data on chain, it assumes that okay, the computation I've done and everything I've done is valid, right? So this kind of takes some like a couple of weeks, and if not like I think a week or two before you can attest for the validity of that computation that you've done off chain. So the architecture is such that common to most layer two, to most layer two, such that you have in rollups now you have the layer two, and then you have layer one, right? Layer two now is, let's say Starknet as an example, and then the layer one now is Ethereum. So you have to have separate smart contract. You have to have a smart contract deployed on layer one, and also have a smart contract deployed on layer two, basically. So every activity, transactions performed on layer on the layer two, the computation, the proof, right, is sent from the layer two to layer one. So narrowing it down to optimistic rollup now, basically, once you, an example is optimism. Once optimism performs those like those transactions and then compresses them, it now sends it, should I say, what's the word to use now? It sends the data, right, in form of false proof to the layer one. But then in the hope that, okay, this transaction is valid, right? So that is where the concept of like the word optimism, like optimistic sort of comes in. So when you submit the fraud proof, right, it's optimistic that okay, this false proof that I submitted is actually correct. But then you have mechanism already in place to check the validity of these proofs. That is why it takes quite a number of weeks and days to validate that proof in optimistic rollup. So during this process in optimistic rollup, you cannot be, so withdrawals cannot like be performed because the smart contract deployed on the layer one basically is to handle for deposit and also withdrawals, and also to verify the proof that are submitted. So this is what optimistic rollup means. Basically, there is more to it, such as how it validates this proof, what happens to if someone submits a wrong proof, right? I think there will be additional resources shared to like check out those concepts. Now, going towards the concept of ZK proof. To understand what ZK proof are, we have to like talk about some concepts such as a concept basically, which is zero knowledge. So I'm sorry, please, any questions so far before I continue? Could you please unmute your mic and just ask your question if you have a question?
Hello? Hello? Hello?
Yes,
I would
Yeah, I
we can
can hear
hear you.
take like 5 minutes to like answer questions. So I don't mind like going back to the slides and explaining some concepts that seem confusing. So if you have any question, please speak up, so others
Hello?
can actually like contribute to what is confusing to you.
Yeah, why do you still have high gas fees sometimes on rollups, even though they're supposed to scale Ethereum?
Nobody. Okay.
Didn't
That
you get
means we
that?
understand
Oh,
blockchain, we understand transactions, nodes.
hello,
If we
Kevin.
don't understand, I can go in there before we proceed.
Hello,
Can you hear
Kevin.
me, Kevin?
All right then.
Can you hear me? I think probably. Wait.
Yeah. So what is zero knowledge? Zero knowledge
Can't hear you, but you
basically
can.
is a way you try and like prove, let's say, the existence of validity of something to someone without revealing too much detail. So an example is let's say you want to like travel out of the country, right? At the airport, you have to show your what do we call it, your passport, and then showing your passport reveals a lot of information about you as a person. I think although those details are actually like required, but then let's just narrow it down that I want to prove that okay, I have I am a Nigerian, I'm a citizen of this country, and then this is my information, right? So zero knowledge is just a way for me to prove the authenticity of the information, right? Without showing too much information, without showing my age, without showing my passport number, without showing my nationality or any information of sort which should like be best known to me. Now, so simply put, so it's a means by which a prover. So there are two parties involved now. So you have a prover and then you have a verifier. Now, a prover in the scenario I gave, I am the prover. I am trying to like prove something to the official at the airport that okay, this is who I claim to be, right? In this case, the airport official now is the verifier, right? So I have to be able to like convince the person that okay, I am who I claim to be. So the zero knowledge protocol uses the statement called witness as an input to generate a succinct proof of its validity. This proof provides strong guarantees that a statement is true without exposing the informations in creating it. Do we like get the concept of um okay, sorry. No, I can't hear you. Can you please unmute your mic and speak? I'm not sure. Okay, Victor, what is your question, please?
Hello, can you hear me?
Yeah.
Okay, so my question, I've just typed my question in the chat, but I can read it out as well.
Okay, why do rollup still have relatively high gas fee, like up to $2 for a swap sometimes on Starknet, and even occasionally on optimistic when activity is high? Only Polygon seems to have consistently low gas fee, like 0.1.0. Please confirm if you can hear me.
Yeah, I can hear
Yeah,
you.
you can hear you. Yeah.
Hello, Kevin. I don't think Kevin can hear us.
Please give me a minute.
Yeah, kindly check if you can, if you're able to hear us, because we can hear you clearly, but you are unresponsive. So please.
So I think the problem is from my PC. I'll check and get that fixed in a bit. Okay. Can someone just speak? Maybe I can hear.
Hey, Kevin, can you hear us now?
Yeah, I can. Sorry
Oh,
about
okay.
that.
No.
Oh, okay.
Perfect. I think Victor can now ask his question. Sorry, guys, for the inconvenience.
Hi, Kevin. My question is just what I shared in the chat, so I am sure you've just gone over it right now. But basically, I think the roll-up, sometimes the gas fees, like they can almost mirror L1 gas fees sometimes. They can go as high as, $2. And the promise of roll-up is to have the gas fees relatively cheaper. So I don't know if that question is too early or you're going to cover it much later in this program, but yeah, so I was just curious about that.
Okay. Okay. Sorry, please give me a minute. I could not clearly hear you. I think I have to make corrections to something. Sorry. I'll make a comment on that in a bit. Give me a minute, please. What do you? Can you please ask your question again? All right. Yeah. You guys can hear me, right?
Yeah, but then it's a bit loud than before. But we can actually hear you.
I did that again. Mic check. Is it better now?
Okay, just increase a bit more, please. I was thinking. Okay, I think it's better now. Yeah.
All right, it's better now. Okay. So to answer your questions, right? I have not seen a scenario where the gas fee is as high as $2 on Starknet, but basically, I think I can't see per se. I can't see basically. I can't see what what could be the cause of that. But I'll just revert back to you and see if I have an answer for you in the next class. Okay. So any other question, please? All right. So everybody, we get the concept of optimistic roll-up, right? All right. So now we've established that zero knowledge is a way to like for a prover to convince a verifier of some particular statement that it holds true without revealing sensitive information. And then should I say types of proof now? We have interactive proof and non-interactive proof. Interactive proof basically means that there has to be some sort of back and forth communication between the prover and the verifier. This sort of limits the system, right? And looking at the non-interactive proof, that involves the prover and the verifier sharing sharing the same key, right? Such that there's just one's interaction, such that, and what I mean by just one interaction is there's just an interaction between the prover and the verifier once, and with the help of the key that they have, you can easily like make claims from the prover can make claims which can be easily verified by the verifier. So there are two major types of zero knowledge. You have like the ZK snarks and then the ZK stacks. The ZK snark stands for zero knowledge succinct non-interactive argument of knowledge. So zero knowledge means that you can prove the authenticity or validity of something to someone without sharing much information. Succinct means that the proof size is relatively small for snarks, for ZK snarks, and then non-interactive means that there is no back and forth interaction between the prover and then the verifier in this case. So looking at stacks too, like we established zero knowledge, trying to like prove something, to prove a prover is trying to prove something to a verifier. And then scalable, it means ZK stacks are relatively like faster compared to ZK snarks, and then they are transparent, they are public to for the system to utilize. So we already established that we have two types of rollup. We have the ZK rollup and then the optimistic rollup. So there are quite a number of use cases for zero knowledge, right? And you can use them in the application layer, right? You can use them at the core infrastructure level, but basically it's just for you to abstract something out that, okay, I am proving this, right? And then someone else can like verify the validity of that concept. So ZK rollup uses ZK proofs by combining a large number of layer 2 transaction, that is, the transaction is done off-chain, into one transaction that gets validated on Ethereum mainnet. So we earlier we said that optimistic rollup utilizes something called false proof, whereas ZK rollup utilizes something called validity proof, right? So so when you make computations on layer 2, right? Let's say we process 1,000 transactions on layer 2. They are compressed down into a single transaction, and then the validity proof, the proof of that computation has to be submitted to the layer 1 and has to be verified by the contract deployed on the layer 1. We'll still see how the layer 2 communicates with layer 1 and how layer 1 communicates with layer 2 basically towards the end of the slide. So the main difference between ZK rollup and optimistic rollup is that instead of assuming transactions are valid until proven otherwise, ZK uses validity proof to prove instantly, to instantly prove if transactions are valid or not, right? An example of platforms that uses these approaches, the Starkware, which is, I think, a parent to Starknet, and then we have ZK Sync. So optimistic rollup are considered optimistic because transactions are assumed, like we established, to be valid until they are proven false. Before optimistic rollup transactions are confirmed on Ethereum main chain, there's a period of time when potentially invalid transaction can be disputed by submitting a false proof. So basically, this correlates with what we discussed earlier, that if once you've done your computation on off-chain, or using optimistic group as an example, once you've done your computation off-chain, then you submit a false proof on-chain, on layer one in this case, and it takes quite a number of days, if not weeks, to like validate the authenticity of that false proof which you've submitted. So that means participants in that network can check that transaction and check that, okay, this proof that you've submitted is invalid or something. But basically, whereas in ZK, when you do the computation, right, the computation is broken down into the simplest one, broken down into polynomials, right? And then basically what needs to be checked is, okay, is this proof valid? If it is valid, it returns a true. If it is not valid, it returns a false. So if it is true, then the proof is accepted on chain. If it is false, it is rejected. So yeah, basically that's what ZK zero knowledge rollups and optimistic rollups are, and the differences between them. Any questions so far? How is decentralization in the context of rollup on layer one? It is the different number of nodes running the client. Does that same applies to rollup? Are there nodes running layer 2 client? So for Starknet, I'll use Starknet as an example. So right, on layer 1, you have nodes, right, that are basically like ensuring the consensus of the nodes and ensuring that state transition occurs as it should be, validating transactions basically. So on Starknet as an example, you have sequencers. Sequencers are, when we get to the architecture of Starknet, you see how this is done basically. But the idea is there is a sequencer. The sequencer could be likened to the node on the layer 1 in this case, but then it has its own specific activities it does, which is different entirely from what the nodes on the layer 1 does, right? So the sequencer does this. I'll explain this in a later part of the slides. I think we've not gotten there. So just bring me back to this question basically. So because Starknet is a ZK rollup, right? It is difficult for it to have like to implement EVM compatibility due to the complex computation it does and how complex the activity is, right? So I had to like come up with a new language on its own, which is like the Cairo language, where you can like write smart contracts in Cairo and then have your sequencer execute this and then bundle those transactions, submit the details to the layer one basically. So the point I'm trying to establish here is you have layer ones, you have layer twos which are EVM equivalent, that is, they are EVM compatible, such that you can write your conventional solidity and everything works fine. But then StarkNet being a ZK rollup takes a different approach where it has its own VM to the Cairo VM, which basically takes charge of executing transactions and then checking for the state of your contract, basically. So so we've established ZK rollups and then optimistic rollup. But then why are we using ZK stacks? Why not utilize ZK snarks, right? We know that StarkNet utilizes ZK stack. What is special about ZK stacks? So ZK snarks and ZK stacks are both non-interactive, zero knowledge. So while ZK snarks have huge advantage when it comes to proof size and throughput, remember we said they are succinct, which means their proof is the proof size would be small, right? This is what this statement is saying basically. So they have two major weaknesses. They require trusted setup and are not resistant to quantum attacks. What do we mean by trusted setup? That means you have to have like you have to have if not like have a collection of people come together to choose a common reference, a CRS, right, which would like be used in the system, right? And this can be somehow, this can sometimes be at a disadvantage because if a third party should get hold of the CRS generated, the common referencing generated, right? That means the system is susceptible to attack. A third party which has this can basically submit a false proof which will like be accepted onto into the network. And so that is basically what trusted setup mean. And also they are not resistant to quantum attack. But then looking at ZK stack solves this problem like very well, right? It doesn't require trusted setup, and it doesn't and it is also quantum attack resistant. But then the proof size is quite large compared to the ZK snark. So those are the differences between ZK snark and ZK stack. You can check the resource page on Notion to dig deep into how ZK snark work and how ZK stack work basically. Any question? Okay, question. So do we have any questions so far before we dig deep into the architecture of StarkNet? Okay, in the absence of no questions, so StarkNet architecture. So you have so on the left hand side now you have a bunch of transactions being processed on the layer 2, right? The sequencers take this transaction and then generates traces, right? And then these traces are passed on to the prover, the sharp prover. The sharp prover basically take these traces and then generates them into a proof. Then the proof is submitted onto layer 1, which is the verifier contract on layer 1 now. And once it is like attested that okay, this proof is valid, then it is submitted into it is then taken to the fact registry basically. So this is like how it works at the lowest level. There are stuff like going on underneath, but this is like at the surface level. You have transactions, being passed to the sequencers, and then the sequencers generate like traces basically, and the sharp prover uses these traces to generate proof, and then the proof has to be submitted to the L1, and then the L1 confirms the validity of this proof, which either returns a true or false. And if it is true, it is accepted by the L1. If it is false, it is rejected by the L1. I don't know, did we get that before I proceed? Okay. So looking at the architecture, yeah, please give me a minute. No. Okay. Sorry. Yeah. Okay. It's a little bit of tiny. I'll just like go back to the slides. Sorry. I was trying to see if I could partition the screen so I can follow the slide at the same time, but it looks tiny. So we have a prover, we have a StarkNet OS, we have StarkNet State, we have StarkNet L1 core contract. So a prover basically a separate process, either online or internal to the node, that receives the output of Cairo programs and generate Stark proof to be verified. In this case, that is like the sharp prover. So then you have the prover submit the proof to the verifier that registers the fact on L1. So once these facts are accepted, they are registered on L1 as we explained here. So then you have the StarkNet OS. So what the StarkNet OS does basically is it updates the layer 2 state of the system based on transactions that are received as inputs, effectively facilitate the execution of Cairo-based StarkNet contract. The OS is Cairo-based and is essentially the program whose output is proven and verified using the Stark proof system. Specific system operations and functionality available for StarkNet contract are available as a core made to the OS. So I should have explained this in. So this line is basically saying that the StarkNet OS is responsible for updating the state of the layer 2, right? And it also like offers you it exposes you some components which you can like use to make call to the StarkNet OS. So StarkNet state, the state is composed of contract code and also contract storage. So StarkNet L1 core contract. This L1 contract, that is the layer 1 contract. So this contract is deployed on layer 1, right? Defines the state of the system by storing the commitment to layer 2. The contract also stores the StarkNet OS program hash, effectively defining the version of StarkNet the network is running on. So what this is saying basically is, we established that for the layer 2, right? You have a contract deployed on layer 1, you have another contract deployed on layer 2, where layer 2 takes the computation, either false proof or validity proof, depending on the roll-up approach you're using, which could be optimistic roll-up, or which could be false proof or validity proof, right? And then submit that to. So the layer 1 contract now, that in the case of ZK rollup now, that takes that in StarkNet is the StarkNet L1 contract. The committed state on L1 contract and L1 core contract acts as a provider as consensus mechanism of StarkNet. The system is secured by layer 1 Ethereum consensus, basically. So in addition to maintaining state, the StarkNet L1 contract is the main hub of operation of StarkNet on layer 1. So every activity that needs to be performed right? Verification, withdrawal, deposit, they are done on like the Starknet core contract. So this Starknet core contract also like facilitates back and forth interaction between layer 1 and then the layer 2, between layer 1 and layer 2 basically. Okay, there are no questions. Awesome. So there has to be a way to ensure that layer 1 communicates with layer 2 and layer 2 communicates with layer 1 basically. So how does this like kind of happen? So this is what we'll like be taking a look at here. So the diagram above here, the explanation is here. So you have the layer 1 contract. So if you want to interact from layer 1 to layer 2 now, so the layer 1 contract calls the send message function on the Starknet core contract. I don't know, please. Is okay. Darlington, please, are you on the call?
Yeah, I can hear you.
Yeah, I was wondering if you could like share me the contract to the core to the core contract on
Hey, Kevin,
layer
I
1.
can actually hear you.
Yeah, I need
Yeah,
some.
Kelvin, I can hear you.
Yeah,
You
could you
said
please
share
share me
what?
the address to the core contract on layer 1? It will take me like longer.
Sure.
Yeah.
Sure, give me a minute.
All right. That should be on StarkScan, right?
Yes, StarkScan, yeah. Just go to StarkScan, then check the developer section.
Okay.
Yeah, then check the address book.
Okay. Thanks.
Okay, I could paste it.
So this is the core contract. I just want us to see the contract and see. I think it's verified. Let's see, read transactions. Transaction, write as proxy. Send message. Yeah. So because I have to like demarcate my screen this time. Okay. You can see my screen, right?
Yeah, we can.
Okay. Share a minute, please. Scan. Contracts. Yeah, so the L1 contract calls if the L1 wants to, the layer 1 that is Ethereum wants to like communicate with the layer 2 in this case, right? So the L1 contract calls the send message function on of the I think that should be send message to layer 2. Yeah, function on Starknet core contract, which stores the message and also like takes a payload, stores the message. In this case, the message which includes additional fields, which includes the selector. So what the selector is saying basically is like the first 4 bytes of the function you're trying to like call on that layer 2, right? So in this case, the message includes an additional field, the selector, which determines what function to call in the corresponding layer 2 contract. So you call the send message to you call to communicate with layer 2. Now you have to like call the send message to layer 2 function here, and we can see that it takes in the parameters, the address of the contract on layer 2 that you're trying to communicate with, the selector, the function you're trying to call. So if, let's say, you're trying to like call some sort of, let's say, deposit or any function, you have to like get the selector. And I think we should all like be familiar with what the concept of selectors are. They are like the first 4 bytes of your function signatures, basically. And then you pass your argument, the payload, the arrays of the payload you're trying to like the payload which the function receive, basically. So the StarkNet sequence automatically consumes the message and invokes the requested layer 2 function on the contract designed by the to address, right? This direction is useful for example, like deposit transactions. So like I have explained, right, you have to like specify the selector of the function you're trying to implement to interact with, and also the layer 2 contract you're trying to like interact with. And also know that while honest sequencers automatically consume layer 1 to layer 2 message, it is not enforced by the protocol, right? So a sequencer may like choose to skip a message, right? So they have like will to like pick messages to like respond to execute, basically. This should be taken into account when designing the messaging protocol between 2 contracts. So we've seen the interaction of layer 1 to layer 2, and also how do we like communicate between layer 2 and layer 1, basically. So an example is here. So messages from layer 2 to layer 1 follows this approach. The layer 2 contract function calls the library function called send message to layer 1, which is like the alternative to when we're discussing about communication between layer 1 and layer 2, which you know that is going to like call the you're going to execute the function called send message to layer 2, right? So you execute this function called send message to layer 1, specify the to address, the destination of the contract you're trying to interact with, and then send and log it with it a payload. So the StarkNet OS adds the from address, which is the layer 2 address of the contract sending the message. So once a state update containing the layer 2 transaction is accepted on chain, right, the message is stored on layer 1 core contract waiting to be consumed. The layer 1 contract specified by the to address invokes the consume message from L2 of the StarkNet core contract. So this is like the process, basically. You execute the send message to layer 1 via the library made available to you by StarkNet, specify your parameters and also the payload. And once the details are gotten on layer 1, then the layer 1 automatically execute the consume message from layer 2, and state transition and everything is like performed. So since any layer 2 can send message to layer 1, it is recommended that layer 1 contract check the from address before processing the transaction. So any layer 2 contract now, like we established that most layer 2s most layer 2, right, they are EVM compatible, which means they don't like need to like come up with their own language. But then StarkNet, which is a ZK rollup, right, is not due to its high computation, right? It's not like compatible with EVM, so it has to come up with its own VM basically. That means you have Cairo given to you as the programming language to write your smart contract and execute your contract logic basically. So what we are saying is, since you have this available, that means you can write different, you can have different product, you can have different protocols, right? That means like different layer 2 contract can make call to the core contract on layer 1. So you have to like check the from address before you execute any transaction. That is like what I'm trying to like lay emphasis on basically. I think that would be it. Sorry, I have quite a number of slides. Oh goodness. Yeah. Okay, so any question? Okay, so I think you mentioned it takes about 7 days to verify completion of optimistic rollup, which is started on Ethereum. How long does it take Starknet? So Starknet is immediate, it's fast, I think within seconds, right? Because we are using basically using ZK proofs, right? And validating the proof is instant, so there's no need to like wait for any day interval or anything like that. So that's like the significant difference between optimistic rollup and ZK proof, like the significant difference between optimism and also Starknet itself. I don't know if I answered your question, Victor. All right, awesome. Okay, so I know like we discussed quite a number of things on in this call. So let's just like take time to like process and also like take time to like ask questions. Or yeah, so any questions so far? I think that is the end of the slide basically. Communication between layer 1 and layer 2. So in conclusion to this slide, we got a brief introduction to like, not brief introduction, like we reviewed what a blockchain is, right? And talked about the layer 1 and also the blockchain trilemma. Why do we need a layer 2 and what are the layer 2 solutions available and how are they implemented? Where we got to talk about briefly, not extensively, touch on state channel, plasma rollups, and then we took it a step further to talk about rollups and how Starknet is utilizing rollups, and also got a bit of understanding about zero knowledge and what the categories of zero knowledge that we have, and took it a step further to talk about Starknet and how Starknet scales Ethereum basically, and also the interaction between the layer 2 and the layer 1 blockchain. So any question so far? And if you don't have questions now, you can always like drop your questions on the community channel. Just tag me. I'll be ready to like provide answers to your question basically. But as at now, any questions so far? Are we all clear on what we like discussed so far? Okay. How does Starknet ensures that we trust the prover not to do anything malicious? Prover. So so the prover can't do anything malicious basically, because you have the computations. Like, let's say, let me give you this example basically. Say you write your contract. Let's say you write a simple storage contract that stores number on the blockchain and then retrieves number on the blockchain basically, and every action you perform is brought down back into a simple computation, right? I think it takes the process of computing it down from RC1 to like polynomials basically. And once you have this, generates the Stark prover generates the proof which is submitted to the layer one. So there is no way in which any sort of malicious activity could occur in that instance, unlike the optimistic rule where you are optimistic, okay, something this computation none is valid, right? And you have to like wait for a couple of days to validate the false proof that is given. I don't know if that answered your question. Any other question? Okay, yeah, I didn't. Okay, no questions. So I guess I'll stop sharing my screen. Yeah. So, Paul, are you on the call?
Yeah, thank you so much for the class, Calvin. And yeah, so I came across a particular question when the class was going on. So someone asked how long will the bootcamp last? Can we have an overview of what we're able to achieve at the end of this class? So I will have Dickens to explain these questions right here. Dickens, can you please unmute and explain this?
Sorry.
Okay, so thank you all once again for attending this first iteration of the Starknet Nairobi Bootcamp. So we made a few changes to ensure that this learning session is benefiting you and you get the most out of it. So as a result, instead of packing the courses or the classes back to back for the next 2 weeks, we decided to have a boot camp at intervals of 2 weeks. So for example, today on 27th, we've had the first iteration. The second iteration will be on 13th March. And then there'll be another iteration, which would be on 27th of March as well. So this will cover the introductory part into StarkNet and into the StarkNet ecosystem. Thereafter, in April, we'll be able now to write code in Cairo and be able to develop smart contracts in Cairo. So we've divided it into 2 sections: the introductory part as well as a deep dive section. So this is to allow you guys an opportunity to go read through more, maybe ask questions more on the Discord channel. So the 2 weeks will allow you to engage more with us, ask more questions, ask more clarification, because on the deep dive section, the topics are quite advanced. So we thought that it would be best if we have a very solid foundation and you have a very perfect understanding of how the ecosystem is, and thereafter we'll be able to proceed. So that is the arrangement as is. I've shared the registration link via chat right now. If you haven't registered for this session, kindly register, because information will be sent via mail on, for example, the next session. Also, regarding how the session will last, what we will learn at the end of the session is always shared via mail for those who have registered. So it's easier also to follow through on that section. I guess that's it, and I'm really thanking you guys for so I've sent the registration link again via chat. So yeah, this number. Thanks. So guys, thank you so much for attending. If you have any question, please, on the registration form, there's a link to Starknet Nairobi, there's a link to Starknet Africa. So please go to those to the Telegram channels, ask the question. So if you've learned something, you haven't understood, if there's a topic you cannot comprehend well, kindly go to Starknet Nairobi, post your question over there, and you'll be answered. So that's how we will proceed from now. So these are clarification on the proceedings of the class. So please remember, instead of having a two weeks back-to-back classes, we'll split it into 3 introductory classes, which will happen after every 2 weeks. So this is the first iteration. The second one will be on 13th. And then in April, with the 3 introductory classes, we believe you'll be in a position to have enough foundational knowledge to be able to dig deep into Cairo and be able to write some code and be able to write smart contracts in the StarkNet ecosystem, and also deploy a contract. So we have a lot of things interesting that are arranged for you. And if there's any feedback that you'd wish for us to share, any improvement that you'd wish for us to maybe improve on this class offering, feel free. The Telegram group is open. As I've said, kindly rush there with your questions. So thank you. Also, there's questions or some sort of an assessment which would be sent to you that will help you prepare for the next session. So you'll be able to dig through the questions and Google more and try to understand more. And then that would be able to enable you to benefit more from the next session, which would be on 30. That is it. Thank you so much. Feel free to reach out to me or call for any information. Thank you.
Yeah, thanks, man. Just like he said, we actually already planned this class to go in over by everyone. We have a solid foundation when it comes to StarkNet, layer 2, ZK proof, and everything about StarkNet. So if you have any question particular about this, you can definitely ask in the chat, or probably after the call, you can always ask in the group. Is there any question here? Okay, that sounds fair. I hope. Yeah, so that's actually what we have in plan. So we are going to send out assessments via email. So in case you don't see the email pop out in the list of your, just check your promotions in your Gmail or any mail you're using. You're going to see it right there. Okay, so this class is actually designed to make sure that you have solid foundation on the classes. Then as well, around April now have a solid deep dive into Cairo. So if there is no further question, I think we are going to call it a night.
Thank you guys. Bye-bye. Enjoy. Have an interesting evening.
Yeah, you too, man. Yeah, bye.
All right, guys. Bye. Thanks for coming. Training.
Yeah.